Now, another thing that astronomers are very interested in measuring is the masses of black holes in quasars themselves. Because the quasars are those black holes that are actively swallowing up or accreting a lot of matter. And we have to use very, very different techniques to study the masses of black holes in quasars, because in the center of a quasar, the quasar light itself is so bright compared to the light of the galaxy that you basically can't observe these stellar motions or orbits of disks of gas in the same way that I've showed you before. All that light is just totally swamped and overwhelmed by the brilliant light of the quasar at the center of a galaxy that's currently in an active quasar phase. So we have to use very different kinds of techniques to study the black hole masses in quasars. And to explain how that works, let me show you just a sort of a simple cartoon of what the central heart of a quasar looks like. So inside a quasar, we have a supermassive black hole with mass from anywhere from billions up to millions up to even billions of times the mass of the sun. Surrounding that is an accretion disk, a disk that is composed of gas orbiting and spiraling into the black hole and heating up tremendously. And that gas, as it falls into the black hole, is radiating away a tremendous amount of energy in the form of X-ray light, ultraviolet light, visible wavelength light. This accretion disk is extremely hot and glowing because it's so hot. And then surrounding that, there is a system of clouds of gas that are in orbit around the black hole. And you can, this is sort of a silly cartoon, but just to illustrate kind of what's going on, these are clouds that are very close to the black hole, and they're orbiting very rapidly around the black hole at speeds of thousands of kilometers per second because they're so close to the black hole. The black hole's gravitational pull is so strong that these clouds are orbiting extremely fast around the black hole. And what happens in a quasar is that all of the ultraviolet and X-ray light coming from that accretion disk will illuminate these clouds, which are mostly made of hydrogen gas. And these clouds will give off light at specific wavelengths in specific spectral lines. And that's great because then we can use these clouds, this whole system of clouds, as sort of a probe of what the black hole mass is, using the same kind of technique that John Mitchell talked about all the way back in the 1700s, because we can actually study the orbit of this system of clouds around the black hole based on the red shifts and blue shifts of light that we see. So how does this work? Well, let's take the light of a quasar and spread it out into a spectrum, and I'll show you a little bit of what we see. So if we take the light of a quasar and spread it out into its constituent wavelengths, going from blue to red wavelengths, like this basically corresponds to the range of wavelengths that your eye can see, going kind of from violet to blue to green in the middle and red at this end. There are a couple of different components to the light of the quasar that you see. One component is what's called the continuum. This is the light that is seen continuously at all wavelengths, and that's the light that comes from the very hot surface of this accretion disk that's glowing at all wavelengths because it's so hot. And that light is illuminating the system of clouds that are in orbit around the black hole, and those clouds then give off light in specific spectral lines at specific wavelengths. And the ones that we're really interested in are these hydrogen spectral lines that come from these clouds orbiting very, very close to the black hole. And what you see when you look at these hydrogen lines is that they're actually very broad. They're broadened out because some of the clouds are moving towards us, and the wavelengths of their spectral lines are blue shifted. Some of the clouds are moving away from us, and their light becomes red shifted. And the whole aggregate motion of this entire system of clouds that's orbiting at very, very high speed around the black hole gives rise to these very highly broadened lines. And from the width of spectral lines like that, we can determine the aggregate speed that these clouds are orbiting the black hole, which in this case is thousands of kilometers per second. So these are very high speeds. And now, going back to John Mitchell's method, if we knew the average distance from the black hole to where these clouds are, then we could combine that average distance with that aggregate speed and get an estimate of the mass of the black hole, the massive thing in the center, at the center of this orbit. And to do that, astronomers have developed a technique called reverberation mapping or echo mapping. And let me just explain to you a little bit about how this method works. It's something that my research group has spent a lot of time working on over the last year or so. So consider a black hole with an accretion disk as just sort of a very simple example, and that black hole is surrounded by just a thin shell of hydrogen gas, just to illustrate a simple cartoon of what's going on. And we are down here at our observatory looking at this system. Now, the accretion disk around a black hole does not shine with steady brightness like the sun. It actually has a brightness that fluctuates very randomly over time because the rate at which material is feeding into the black hole is constantly fluctuating and changing over time. So the brightness of a quasar goes up and down quite randomly over time. And the system of clouds that are illuminated by the black hole, their brightness will also go up or down over time in response to that because they're being illuminated by the light from that central engine. So consider a situation where the brightness of the central engine, the accretion disk, suddenly goes up because more mass starts spilling into the black hole. Well, the light from that central engine then will propagate outward to this shell, and it'll take a certain amount of time to propagate out to that distance because light travels at a finite speed, at the speed of light. So if we could measure how long it took for light to get from here to here, then we would know the radius of that region. And we can actually measure that because what we see when we observe this object is the light that comes to us from that object. And what we see is that if the brightness of that central source changed in time, that signal would have to propagate outward to this shell, and then at some later time, we would see the brightness of the light from that shell also change in response to the earlier change in the brightness of that central source. So if we measured the brightness over time of the continuum light from that central engine, and if we measured the brightness over time of the spectral lines coming from the clouds of gas surrounding the black hole, we might see something sort of schematically like this. If the central engine suddenly increased in brightness, we would see that the emission line brightness would also go up, but it would be a little bit delayed in time and sort of broadened out in time because of the time that it took for that light signal to propagate from that central engine out to where those surrounding orbiting clouds are. So this is the basic method called reverberation mapping, and astronomers have used this method for about 20 years now to determine the structure of the central regions of about 35 different quasars, mostly at sort of moderate to high black hole masses, typically around 100 million solar masses. And our group was very interested in applying this method to learn more about the very small black holes in the mass range of around 1 million up to maybe around 10 million solar masses, where we really just didn't have very much information on the population of black holes in that mass range at all.